Okay, questions? Yeah, don't mind. Don't worry about repeating the question. That's okay. So you may not be here yesterday. So yes. In the practice, which one? You mean the everything or? Sure. Let me go to the question first. Okay. The question was the practice question you were given for the exam. Okay. Let me first of all go to my lectures page. Yeah, we can go over that for sure. Okay, 2030, and then okay, and then I'll go to the end over here. Let me go to solution directly. The solution. Yeah. Okay. Which question are you talking about? Question 4. Oh, you mean this guy here? Okay. Okay. Let me do a little bit of sketch together with you to see what happened. Okay, no problem. Okay. Let me first of all get this guy here, and what I'm going to talk about will just be consistent with the solution. So you can also look at that. Okay, let me do it again. Just want to copy the thing. Okay. Okay. Okay, this is what you were given for question 4. Okay, so apparently you have like a triple nested loop, right? Again, you shouldn't really just tell me it's n cubed right away just because you got 3 nested levels. That's not the way to go. Okay, let's say you're given this on the exam. You don't have to really derive like a calculate a precise number of primitive operation. You don't have to, okay, unless we tell you to. I think for this particular question, what we really want to see is whether you can figure out a pattern of changes on the loop counter, right? Okay. Let me get to the point. So now you can. I'm gonna say let's look at 3 different headers over here. You can see we have a header over here. Okay, number 1, and also we have another header over here, number 2, and that's number 3. Okay, 3 headers. Okay. Before we look at the headers over here, let's look at the body of the loop. Okay. So now, if you look at, let's see this, okay, this line here. Okay, that's the body of the loop. Okay, so now you can see over here, this is the body of the loop. Basically, if you're just able to see exactly what the body of the loop is, figure out what's the running time for the body of the loop, which means it will take this much for each iteration. Okay. If we only look at line number 5, what will be the running time for that? 01, okay. Apparently, we only try to print something and also doing the arithmetic, so that's very primitive, okay. Body of the loop, you can see it's all about arithmetic, so big O of 1. So now we can know that the running time overall will just be the big O of each iteration is going to take 1. And then multiply by the number of iterations. That's going to be the overall picture, right? So now we want to figure out exactly how many iterations we have overall. And that's going to be decided by I, J, and K. Okay, so that's the key. Okay, I would say let's start with the pattern of changes for I and J. The K simply just go a little bit further. That's something you're not so familiar with, so we'll go over that, okay? Just to get an idea. Let's be very careful over here. So that means, let me say, first of all, let me start with I. The value of I, so starting from 0 until n minus 1, agree? Because as soon as I gets to n, you're going to exit from the loop. So I equals n is not going to be used. I would be 0, it would be 1, it would be 2, all the way to. So the last value for I would be just n minus 1. Okay? So the outer loop is going to run n iterations, okay, from 0 to n minus 1, okay, first of all. And then we're going to look at j. That part is also not too bad. if we look at j over here, it's going to be from I until n minus 1. Okay? So now if we talk about j now over here is going to be, for I is equal to 0, it's going to be from 0, 1, 2, all the way to n minus 1. Okay? Good. And also for this guy over here, when I is equal to 1, it's going to be 1, and then 2, all the way to n minus 1. And for I is equal to 2, it's going to be 2, and then n minus 1. Okay? So the indentation, hopefully that helps. Okay? Finally, when I is equal to n minus 1, it's going to be just n minus 1. Okay? So that's the middle loop. I'm talking about line number 3 over there. So now let's see how we can bring k into play. Okay, it's not too bad. Okay. So now let's talk about k. I'm going to use maybe green over here. Okay, k over here. And k somehow depends on j. You can see k is initialized to be simply just j, and then it's going to be k minus minus. Okay, the minus part is really important over there. Okay, so what I would do is let me try to figure out the k. Basically, for every value of j, you have to worry about how many iterations you're going to have for this inner loop over here. So now we talk about this one particularly. Okay, the green one. Okay, so now when j is equal to 0, k will definitely start with actually 0 over here, but do we actually use this 0 over here? We don't, because we say larger than 0, right? Good. Okay, so we don't need that. Okay, let me just get rid of it. And then when j is equal to 1, k will be just 1. Because when the second iteration, when k gets to 0, it's not going to be used, right? Okay, so I'm talking about k over here. And now let's do the similar situation. So now it will be 2 and then 1. Agree? And then over here, this will be n minus 1 all the way to 1. Okay, let's do something similar. Okay, so now when j is now equal to 1, okay, so now it will be just 1. And then this one here will be 2 and 1. And then here it will be n minus 1 all the way down to just 1. Okay, and also let me just finish that. 2 and 1. And then n minus 1 and then 1. And this one here will just be from n minus 1 all the way to 1. Okay, are we okay with that? Okay, so now we just have to figure out exactly the pattern of doing this, right? The way to figure out the pattern really is by observation. Before you can do the observation, you got to do some examples. So why don't we do some example over here, okay? Can you tell me the sum of, so you can see for this guy here, let me be more precise. For this particular guy here, we are only running just 1 iteration, agree? And then for this guy here, we are running 2 iterations. And over here, we are running n minus 1 iterations, right? So now to really calculate that, so now let me just put it aside over here. Okay. So what I will do, I'll set it aside. I'm just trying to help you identify the pattern. Okay, I'll put this guy here. Okay. So now let me just say when I is equal to 0, and we're going to get 1 plus 2 plus all the way to n minus 1, right? Okay. And then we're simply going to have 1 plus 2 plus all the way to n minus 1. And you pretty much know how to calculate this sum already, right? Okay, let me just do that. Okay, I'll just write out the formula so you can see the pattern. So it's going to be like this. It's going to be n minus 1. You know what? To really make the pattern a little bit easier to see, if you don't mind, I will just put over here 0. But 0 doesn't really add up anything, but it will help us to identify the pattern. So that's why when you see the solution, I also include this 0. Okay. So let's see this. Okay, let's talk about 0 plus 1 plus 2 all the way to n minus 1. Okay. So now the front is simply 0 plus the end is n minus 1. Multiplied by the number of turns. How many turns do we have in this case? If you include 0, let's say. N terms. Good. Thank you. And then we're going to have n terms. And then, if you don't mind, I'm going to rewrite it a little bit. Would you agree n minus 0 is just n? Okay? Divided by 2. Like that. Okay? Any question about the summation when I is equal to 0? Okay? Of course, how do I know I should rewrite the stuff? Well, it's kind of according to experience. Because when you do math, you got to be a little bit creative when you have to try to identify the patterns. Okay? Okay, so now let's try I is equal to 1. Okay? When I is equal to 1, so what I will get is, so now I can do, this particular one is 1 iteration. And for this one here is 2. All the way to here, that'll be n minus 1. Okay? So now the front will just be 1. The end will just be n minus 1. So now I can do the following. 1 plus the n always seems to be always n minus 1. Multiplied by, we got n minus 1 term, agree? Okay? So now I would say n minus 1 divided by 2. Okay? Guys, have you seen any pattern so far? Give you a little bit of hints. Look at the green one and look at the pink. For example, somehow this 0 here and this 1 here somehow correspond to some terms in the summation. Can you see that? So this 0 over here is somehow used over here. And it's also used in the minus 0 over here. And also this 1 here, also used here, and also use a minus 1 here, right? That's kind of the pattern we identify, okay? You can also do this guy here as an exercise. Okay, I'll leave that for you, okay? Let's say we go all the way to the end. How would that be, okay? The last one is just going to be just when k is equal to n minus 1, just 1 iteration, okay? But how do we express that in the same pattern? So we go all the way to I is equal to n minus 1. Okay? It seems like we have to put n minus 1 over here. Oh, let me use a different color. Okay? So now because we talk about n minus 1, so this guy here should be n minus 1. And plus, the n is always n minus 1. Multiply by, oh, sorry, I got something wrong. Let me write it again. Sorry about that. So did I actually get it right? I think so, sorry. So this would be n minus 1. Yeah, sorry, I just confused myself. So n minus 1 here, so n minus 1 here, no problem. And the n term is always n minus 1. I will also put it there. Okay, so now multiply by, so now this one here should be n minus 1 instead, right? It's going to be n minus n minus 1. Looks fancy, but it's simply just 1. Okay? And then divided by 2. Okay? So now, this would be the final one. If you try to simplify that, you will simply just get just 1. Okay? All right. So guys, any questions so far? Right? This one is slightly more complicated because we add one extra level of complication, just k. Yeah, question?
So the left side would be the orange, and the right side would be multiplication.
You mean the left side? What do you mean? The left side here?
No, the left side of the thing to be divided by 2.
Oh, you mean here?
Yeah, so it's like the n minus 1 plus n minus 1
Okay.
is actually
Yep.
j. And the other side.
Yeah, basically, well, this term over here is just calculating how many iterations overall you're going to run. Right? Don't lose the big picture. Think about what we are doing here. Somehow we are saying that for every particular value of I, which can be 0, 1, or 2, all the way to n minus 1, for every particular value of I, how many iterations are we going to run? Right? In order to see that, we had to see the pattern of changes for j and k. And then we just aggregated that. It's going to be 0 plus 1 and plus 2. Why 2? Because it allows when k is equal to 2 and 1. So that's why it's 2 iterations. So if you add it up together, for every possible value of I, you have this particular formula, which looks like this. Let me just go a little bit further, and then I can take questions. Okay. So now, afterward, we know that if I do a sigma over here, okay, just back in high school math, right? So now I can be from 0 over here until n minus 1. Okay? And then what we just identify is I can just appear over here as a pattern. Okay? So it will simply just be, okay, so 2 is always here. So now I will just be here, and plus n minus 1 is always the end term, right? You can see it's always the end. Okay, always the end. And then parenthesis multiply by n minus I. How do you know this formula works before we try to calculate it? It simply works because if you try to plug in I being just 0, you will see exactly this term if you apply this into this formula here, right? When I is equal to 1, if you apply that into the same formula here, you will get exactly this. That's why it works. Okay, that's how we observe the pattern. I would say in general, for any nested loop you're having, this might be the best way to really figure out the complexity. Okay, anyway, let me go a little bit further. So now what you can do is you can also look at a solution. I'll just sketch how you can finish this up. What you can do is you can try to simplify this just a little bit. Okay, according to the solution, if you do a simplification, this is what you will get. Something like this. Okay, you will get n squared plus I minus 2 times n plus 1 divided by 2. Okay, that's actually some term over here. And then you just want to see what's the highest term. In this case, that'll be n squared. Okay, yeah, sorry, let me make it bigger. You will simply just n squared, but now don't forget, we're going to consider for every I, which would be n possibility. So that's n times n squared. Okay, make sense? Yeah, I would say don't worry. You can feel free to try to redo this particular pattern analysis yourself. If you still got stuck, you can ask me again. Okay, all right. Guys, any further question about this exercise here? So what did we learn from this exercise here? Let's say in the exam, if you are given maybe either double nested loop or triple nested loop. So the best way to do it is to jot down exactly how the loop counter is going to change and then observe the pattern. Once you observe the pattern, you can formulate a summation series and then you can add it up. Okay? Yeah, this one is slightly harder than your lab 8, but I think it's worth doing. Right? Yes? How about no more difficult than this? If that makes you feel relief. Okay. Less than or equal to, exactly. Not strictly less than though, right? Okay. But if you're okay with this, I think you're set for the exam. Yes. Yeah, that's why I just want to put up this slightly more complicated one so you can struggle a little bit before the exam, right? Yes? Oh yeah. So apparently, to be fair, when I wrote a solution, I sat down and then I have no stress, right? I can write it out more properly. In the exam, I would say as long as you can show the work like this, and the TA should be able to give you full marks. Yes. But of course, it's got to be very clear. Okay. I'll tell you what's really important when the TA or myself is going to read your answer. We understand you are under stress, so the answer cannot be so nicely organized. So what do we look for? Okay. Okay. Number one, you should really identify what's the complexity of each iteration for this particular question. Number one, we should see somewhere here. Okay. Number two, you should somehow show some work about how you derive the pattern of changes so we can see your sketch. Yeah, something like that. Yeah. I know many of you actually use a table for your lab number 8. That's also good. Okay. Just make it as organized as possible, right? And then once you have things like this, so now you can make some conclusion to say, so now I can summarize the pattern as this. And then, so this is my final formula. I would say if you can already get to this part here, you already got almost all the marks, right? Yeah, of course, simplification will be nice as well. Yeah. One thing though, you don't necessarily have to simplify. Let's say if you already got this, that's already good enough. You don't necessarily have to simplify it to get things like this. So once you get to this stage, you can simply say the highest term for this term here is simply n squared. So that's why if I multiply by the number of possible value for I, n, so I get n cubed. That'll be good enough. N cubed. We want to show some reasoning over there, right? Yeah. Okay. Yeah, make sure you also know how to prove. For example, how do you prove 3n squared plus 7n minus 2 is actually big O of n squared, right? Things like that, what we also did it yesterday. That's simple marks you should be able to get. Right? All right. Yes? Sure, which one? Which part? Okay, are you talking about the green or the orange? Green? Okay, are you talking about this part here? Oh, yeah, absolutely. Sorry. The green, okay. Are you talking about here? Okay, no problem. So let's just do one, because all the rest are similar, okay? Let's say we do this guy here, okay? When I is equal to 0, okay? When I is equal to 0, we know that j can be from 0, 1, 2, all the way to n minus 1, right? I until n minus 1. Okay with that? Okay. For every possible value of I, that's why it's nested. Okay. For every possible value of j, every possible value for j, you also have k starting from j until actually go counting down all the way to 1. Okay. So for example, let's say when j is equal to 1, in that case, k will start with just 1. But when k gets down to 0, you don't have anything to use because you already exit from the loop. When j is equal to 2, the possible value for k would be 2 and 1. Okay? So here we talk about 2 iterations. Right? And then over here, we got n minus 1 being j. In that case, k will be initialized to be n minus 1 and counting downwards until you get to 1. So that's when you got n minus 1 iterations. So what we're trying to say here, we're trying to say the following. When I is equal to 0 for this particular outer loop, over here, j and k altogether tells you you're going to run 0 plus 1 plus 2 plus all the way to n minus 1 iterations. That's what we are saying. Okay? So now how do we sum this series together, right? Again, I do want to mention it quickly. Whenever you got any arithmetic sequence, if you got a1 plus a2 all the way to an, okay, n terms, for example, right? The way to do it is by the beginning plus the end multiplied by n terms divided by 2. That's a formula. Of course, the number of terms might be different depending on which series you're doing. Let's say for this guy here, for the convenience of summarizing the pattern more nicely, I just included 0 in the beginning. Okay, so now what we got is you got 0 over here. You got that's the first term. The final term is n minus 1. So that's why I put n minus 1 in here. And then from 0 to n minus 1, we got n terms, right? And the way I write n is say n minus 0. So now you can see these two numbers over here nicely correspond to the current value of I. Right? If you go to the next one there, you will see 1 here, and then you will see minus 1 here. Also nicely correspond to the current value of I. Right? That's why we got a pattern. Yeah, that's the beauty of math. Make sense? So what's the best way for you to practice this kind of question? I would say if you believe you kind of understand what's going on here, okay, copy the answer, grab a piece of paper, write it down yourself. Especially you want to make sure you can really reproduce the way we patternize the changes. That's really important. Okay, let me give you another exercise. How about that? Bonus. Okay, I'll change that just a little bit. I think in practice, you wouldn't get any loop that's more than 3 nested level. It's not normal, right? If you really got a 4 nested level of loop, that's not really common. Okay, but anyway. What about if I do the following? So exercise for you. Let's say over here, okay, how about that? Basically, I just changed the way k is going to change. It's going to be k less than n, and now k plus equal 2, which means the way I grow the k counter is going to be, rather than by 1, it's going to be by 2. Okay? That could be slightly more complicated, but give it a try. If you really find this a little bit too complicated, I would suggest start with something slightly more gentle. Either you can try k plus equal to, or you can say k plus plus. You can try with that first, okay, and then try k plus equal to, okay. Maybe try with k plus plus first, okay. 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 Any more questions about this pattern here? We okay? Yeah. You have to do quite a bit of exercise like this in 2011 if you're taking it next semester. Because in 2011, you will have to come up with different data structure algorithms yourself, and then you got to justify the running time. I wouldn't teach you your 2011 if you are taking that in the coming semester. But as far as I know, a very typical exam question could go like this. They would say design an algorithm for problem X. X can be anything. It can be sorting something or trying to find something, right? Such that the running time of your algorithm is, for example, n log n, for example. And they would say, if you got a running time for n squared, you get 50% of the marks, something like that. That's what they usually like to put it. Which means you will get partial credits if you can come up with an algorithm that works, but it's not so perfect in terms of running time, right? So that means running time in 2011 is really important. As we explained yesterday, having n squared versus n log n is very, very different, especially when the input size n grows very large, right? That's kind of the thing you have to worry about next semester. We're going to connect it a little bit. Okay. All right. Any more questions? Emma.
It says that there's going to be like Javadocs and unit testing. Like what aspect of that?
Okay, good. I would say, oh, it's good that you mentioned. Okay, two things, Javadocs and unit testing. Okay. For Javadocs, you have to know how to read Javadocs. I'll prepare some, actually I do have some slides from the previous course. I'll prepare something maybe for Thursday, the final review session. But let me mention that quickly. So things like, remember in every lab that you were given, except for lab number 8, of course. Whenever you're given a method, for example, void some method over here, you got some parameter over here, and then return something. Oh, let me say return something. Okay, just make it a little bit more interesting. Let's say you actually got string over here. Okay, and then maybe something over here. Okay, so what kind of a Javadoc should you know about? Okay, so you should know about, for example, add param, which means each parameter should have a Javadoc, right? Also, you should know about add return. Okay, which is the return value over here, and also I believe you got add throws, right? Like what kind of exception can be thrown from the method? Okay, another one which we didn't quite mention in the class, but I just want to stress that. Okay, that might be useful too. Add precondition. We didn't quite talk about precondition per se, but I can think about precondition as simply something you can assume when you execute a method. For example, I'll give you one example. Precondition simply means something we can assume. Okay, give you one example right away. Let's say we have a method called divide. Double divide. And then I have over here, I should really write it a little more, sorry, better. Let's say over here, we have double divide, and then let's say we got also double x and also double y. So we got two parameters, right? Let's say this. So there are two ways for you to handle the fact that we don't want to have division by 0. Agree? So which means y should not be 0. So you basically got two options. Okay, I'll just mention verbally and then I'll write it down for you. you have two options. Option number one, you're going to say if y happens to be 0, I'm going to throw some exception, like what we did previously. Okay. Number two, you kind of rely on the caller of this method to always not to give you 0 for y, which means you don't check it. Okay, I'll show you the difference. Okay. Might be good if I try to do this in the next slides, and then I'll come back here. Okay, sorry. Okay, I'll give you two options over here. Either one is fine. Okay. Option number one, let's do the one we are familiar with. Option number one. Okay. So now let's say we have this. And then over here we can simply say if y equals 0, okay? And then we can say throw new, right? Remember what we said about exception, right? The basic one. Throw new, just make it simple, I say exception x, okay? Just some error. Okay, otherwise you can return x divided by y, okay? Of course, remember the catch will specify requirements. So here we might just say throws exception x. Okay? How do you write a Javadoc accordingly? So what you have to do is something like this. Okay, so to start over here, and then you would say add param x and put some description about x, and also add param y. You put some parameter for y, put some description for y. And then finally say add throws. Don't forget, you should also say add return. Okay, you can also write it down. So now throws over here is important. You say throws x when something happened, right? That's option number one. That's something you're familiar with, okay? Which means I don't quite trust the caller who actually calls this particular method over here. So I want to make sure if they really gave me y value being 0, I'm going to throw my own exception. I don't trust them. Okay? It's more defensive in some way. In some way, this is said to be more defensive. Defensive about illegal value passed by the caller. Okay, let's talk about option number 2 quickly. Okay, for option number 2, we can be a little bit less defensive. Okay, for option number 2, what I will do is I'll put it here. Okay, option number 2. So what we can do is we can do the following. Okay, we're just going to say here. Okay, let me just write it down. So double, and again we got divide. Again, we got double x. Also, we got double y. But now, we don't have to be defensive about the value that's being passed. We can simply do return x divided by y. Okay? And then, so now how should you update the Javadoc slightly differently? Okay? So still, you're going to have return, of course. You should also have the param. Also, you should also have param x and also param y. These are the same as before, okay? There's another one, I just don't have space. You say add precondition. And then you would say y equals, y is not equal to 0. So precondition simply means under what circumstances can you call this particular method? Okay? So now you would say precondition is y is simply not equal to 0. Okay, let me annotate that. Under what circumstance can you call divide? Okay, that's it. Okay, so now we got these two options. Basically, when you have the precondition tag over here, the consequence is you don't have to do as much like an if then else, try and catch kind of stuff. exception handling as you will have to do if you simply got throws. It's a different ways of designing your code. Okay. And now one more thing to say. Okay. Now, so that means in the beginning of your line over here, now we can assume y is not equal to 0. Okay. Yeah. Question. Good question. That's a very good question. So I would say, okay, I'll try to address that. I know you're going to ask. Okay. First of all, we know that for option number 1, if you really give y as 0, it's going to throw some exception. No question about it. Okay. I would say you only choose option 2 when things are pretty much under your control. So what do I mean by that? Okay. We'll talk a little bit more about this in the software design course, a little bit more advanced later. But I'll just give you some idea. Option number 2 is when things are under your controls. Under your control. Okay, what do I mean by that? Let me put it here. Okay, I'm going to give you some example for option number 2. Okay, let's say this. Maybe I will simply declare. Let me say this. Let's say this is my particular class, and then my class. Okay, and now let's say I simply declare this particular method to be private. Private simply means only the current class can use this method. Any other caller outside this class, they cannot call this method. It's all completely private. Okay. So now let's say I have, void m1. And also here, let me bring that into context. Private, and also double and then divide, right? So that's the method we're talking about. First of all, the fact that we declare this particular method as private, that means only my class can use it, right? No other classes. So it's somehow under the control of my class, okay? And then over here in M1, okay, let's say this, okay? Let's say over here, we're simply just trying to say, let's make it very dumb. Let's say system.out.println. I will simply call this particular method here by saying over here, divide, I will say input over here, and then 10. Okay? Basically, what I'm trying to say is here, the only place I'm trying to use this particular divide is only in this line of code in my class. So it's guaranteed. The only usage for this particular divide is guaranteed to have no 0 for y. So that's kind of under my control. So I can make that precondition. Okay? However, if somehow the method is completely public, in that case, you cannot rely on the caller so much. Yeah. Okay, I'll summarize very quickly, and then I'll go to unit testing. Okay. So now let's talk about this. So option number 1, you know pretty well. The catch will specify requirements, right? Throws. And also for option number 2, if you only have the precondition over here, that means you don't have to write any throws, kind of exception handling kind of stuff. That's kind of easier. However, you may have to, for example, if somehow you want to reason about your code for correctness, in that case, you have to assume whatever that's under the precondition over here. So now, how do I know if this particular division is correct? I know that it is correct because y is guaranteed not to be 0 by the precondition. Okay. So that's about the Javadoc. Javadoc?
No, it's not an exception actually.
Yes.
I noticed that when you throw an exception in the body, and sometimes you don't specify the throws keyword, the compiler doesn't complain, and other times
Okay, good question. Okay, now this part is not it's not required for the exam. I'll mention that briefly. Okay, yeah, don't worry, this part is not going to cover in the exam. I'll just mention that. Okay. In Java, the question was, when you say throws in your method, you don't necessarily have, when you say throw in your method, you don't have to say throws in the API, not necessarily every time. Okay, here's the difference. Java, so now since we talk about inheritance, we can talk about inheritance hierarchy. Okay, there's something called exception, which is a class. Okay, And then there is a subclass called runtime exception, I believe. Okay, so this is some existing class. This is just another existing class. Okay, so now here's a funny thing about Java, which is very confusing. Okay, I'm glad we didn't cover that quite. Okay, so now since you're finishing this course, I can tell you a little bit more. But again, it's not covered in the exam. Okay, for this part. What we did in the lecture, we say in order for you to create your own exception class, for example, let's say negative radius exception, the way to do it is by saying the negative radius exception is exactly extending exception. It's right underneath. It's direct child. Okay. For example, negative radius exception. Okay. Any exception class you create that's directly under exception, they have a name. It's called checked exception. So check exception is any direct child class of exceptions. And in this case, you have to be subject to the catch or specify requirements. Okay. Okay, so this part is what we did in the class. Okay. What if the exception class actually comes from direct child from runtime exception? In that case, they have another name. It's called unchecked exception. Okay, I'll write it down. Over here, so now, for example, one of the examples is called illegal argument exception. Maybe that's what you saw, I guess. Okay, illegal argument exception. Illegal argument exception. Okay. And for this one here, they have also another category name. It's called unchecked. You can think about it's any descendants of runtime exception. Okay, so now what do I mean by that? Okay, let's just see a very simple example. Okay, let's say we got this negative radius exception already. Okay, so now let's say if I have void some method here, integer and radius, right? I can say if the radius is less than 0, so now I can say throw new. So what can I pass after the throw new? I have two options here. I can either give a check exception or I can give an unchecked exception. But the consequence will be different. Okay? Let me do what we are familiar with. If I say throw new, negative radius exception, which is exactly over here, right? It is a direct child of exception, so that'll be subject to catch or specify requirements. In that case, I'll be forced to put throws over here. Negative radius exception. Okay, are we okay with this part? Okay, this part is easy. So now, let's see another option here, okay, which we didn't say. That's why it's not covered in the exam, okay? If I do another one here, let me say purple, okay? So now I'll put it here. If I got void over here, and also m, integer the radius. If I say if r is less than 0, so now I can say throw new illegal argument exception. You can see the only difference is over here. I'm throwing dynamic type illegal argument exception versus dynamic type over here, the negative radius exception. But now in this case, because it's directly under runtime exception, so now the catch or specify requirement is not imposed. So that means in this case, you don't have to say throws. It's a very subtle details. Yeah. Yeah. Conceptually, it's not really worth mentioning, but it's just something to do with inheritance hierarchy, right? But it might be useful if you got to complete some programming assignment for 2011. Anyway, this part is just for your knowledge. Oh yes. So after, okay, that's about Javadoc. So you only have to know how to read the Javadoc. So the other question was about the unit testing. Okay. For unit testing, okay, again, you have to know how to read unit test in JUnits. Okay. I think for this part, we covered quite thoroughly in the JUnit lecture. So maybe just read through all the test cases. I think it's good for your knowledge anyway. Okay, read the and you do not have to write any JUnit test per se. Okay, no need to write any JUnit test. However, let me refer you to this guy here. I think that'll be useful. Although 2030 is not really like a software testing course, but we do expect you to have some independence to actually come up with some test cases. I'll give you one example, okay? And then we can talk about it. If you recall, one of the, let me go to the example over here. Okay, bear with me. I'm going to find it out. Do you remember this particular example for the counter? Let's see this. Okay, let me also point to you the diagram I have, okay, that we did previously. Okay, bear with me, I'll find it out. That should be in one of the very early lectures where we talk about unit testing. When I show you some finite state machines. Okay, I think I'm getting there. The diagram. Okay, I think I'm getting around here. Okay, just give me, okay, there we go. Do you remember this diagram here? Oh, sorry, I forgot to switch. Okay, my bad, sorry. Thank you. Do you remember this diagram? All right. Any recollection about this? Roughly, maybe, vaguely? Okay. So we basically talk about a counter example, right? When we talk about JUnit test. Basically, you have a counter there, and we say that counter should have a boundary between the minimum value and the maximum value. Let's say it's between 0 and 3. Okay, so here's a question that can be possible on the exam. Let's say we have this particular counter with the minimum value being 0 and the maximum value being 3. Okay, in order to thoroughly test it, how many values do you need? How many? Well, apparently 4, right? You can see 4 states over there, right? So you can see you need to test when the value is 0, the value is 1, the value is 2, and 3, right? And then for each one of them, you have to somehow think about what methods you can call on that particular one. For example, you got to see the value is 0. Now you can do increments or you can do decrements. They're going to have different consequences, right? And also, when the value is equal to 1, you can either do increments or you can do decrements, right? Things like that. You may want to study this example again, okay? So now, for example, if I give you, say, now I have another counter. Oh, how about I give you one exercise here? Okay, let me go back to where we were. Okay, give you a little bit more exercise here. Let's say we got 2 counters. Counter number 1, the minimum value is -1. The maximum value is 3. Okay. Counter number 2, the minimum value is, let's say, 4. and the maximum value is 7. I just made it up, okay? And for each one of them, you can also do increments or decrements. And then one more thing. Initial value for counter 1 simply is 0, okay? Initial value for counter 2 is, let's say, 4. So now the question is, in order to thoroughly test these two counters working together, how many test cases do you need? Why don't you think about it? I'll discuss it again on Thursday, okay? You don't need any JUnit test. I just want conceptually how many test cases you need. Okay? Think about it, okay? But you can definitely find hints back to the lecture, the earlier lecture about JUnit testing. You can see that, okay? It's just a little bit more, adding some extra complication. Okay, so about the JUnit unit testing here. So there's no need for you to write JUnit tests, but you want to come up with test cases, okay? Given problem come up with test cases. Actually, number 3 is the kind of very popular interview questions where you go for maybe co-op or internship, or the real job later. They might simply say, now, consider, for example, let's say, oh, how about this? Consider this wireless microphone over here. How would you test it? We can brainstorm a little bit. How would you test it? Microphone there. I'll give you a little bit more information. The microphone there, oh, you know what? Let me make it even easier. The keyboard here. How would you test it? Let's say the setup is the keyboard actually got this many keys, got numerical keys, got a character key, and also it has a USB connection. What kind of test cases do you want to have? There's no Java code, no C code you have to write, but what kind of test cases do you have to come up with? Just brainstorm a little bit. Yes?
First, to check if your computer recognizes the keyboard itself.
That's very good. Oh, number 1, let me just stop you a little bit, Andrew. What Andrew just said, you have to, number 1, to see if your computer can recognize the keyboard. Let's elaborate on that a little bit further. What do you mean your computer? So now you want to be, so when you do the testing, you want to say, okay, I want to test for Linux, I want to test for Macintosh, I want to test for Windows, I want to test for maybe even mobile devices, right? So now you want to be enumerate all the popular platforms. Even for Mac, which Catalina or the previous version? When you talk about Windows, Windows 10 or Windows XP, right? You see what I mean? So you got to talk about different configurations. Okay, go on. Anything else? Okay, let's say we, yeah. Uh-huh. Okay, so every single key. Okay, I'll test maybe all the alphabets for English, A to Z. I also test all the numbers. Okay, how do I know if Control C work or Control V work? That's not just a single key. Also, you want to try maybe different key combinations, right? Yeah, that's kind of the idea, right? So now, if you're given question, well, it wouldn't be as complicated as this. That's quite like open-ended question. I just want to throw it to you. Okay, so that's actually one of the questions Microsoft asked before. How do you test a Dell keyboard? Okay, so now in the exam, we might give you some simple problem, which you may not have seen before. What's the strategy? Okay, the strategy would be, number 1, make sure you understand what the problem is. Okay, don't rush to think about how to come up with test cases. First, make sure you understand what the problem is. Okay, read the description. Okay, and then you want to apply, basically brainstorm a little bit. What should you test? I think the question on the exam is quite obvious to you what you should test, but you want to just understand the problem first, and then think about the test cases. Okay, yeah, that's about unit testing. Okay, Javadoc and unit testing. Make sure you review them quickly. Okay, they should be quite easy. Yes. Yeah. For example, well, I would say I would say the things that we cover in the lecture is actually quite worth reviewing. Okay, I'll just think about what's on the top of my head first of all. Okay, you can ask me some specific questions. You should know what a bucket array is conceptually. Okay, just an array of buckets, right? And then you may have a collision. And then what does it really mean when you override the hash code? What's the default definition for hash code? Guys, what's that? Huh? The address, very good. Okay, maybe you want to review the example we cover in the lecture, right? Okay, overriding the hash code, and also, how do you can you actually simply use the hash code as the definition for equals? It seems like you cannot, right? Why? Think about it. Okay, and then you may have to review how to use the hash table or hash map that we talk about. We talk about actually both, right? We talk about hash table when we talk about hash code, and also when we talk about Java collection, we also talk about hash map. So review both. Okay. How to read the code, basically. And for example, if I override the hash code to be something modulo 13, right? You should know how to calculate the corresponding index to be used, right? That's also something we talk about in the class. Okay.
How do you actually pick, this correct hash function?
Oh, how do you? Oh, good question. Okay, no worries. Okay, so the question was when we talk about the definition for hash code, how do you calculate that, right? First of all, conceptually, okay, again, given any key, okay, key can be integer, it can be string, or it can be any objects, given any key in general, okay? We don't want to use the key right away as an index. What we will do is you will say k.hashcode. That's a hash function. Okay. I'll get to your question in just a moment. And then whatever you calculate over there is going to be used as an index. Okay. So k.hashcode is just going to be the index over here. And then you're going to store something over here. And it's going to be a bucket because you might have collision, because different key objects might give you the same hash code. That's normal. Okay. So Andrew's question was, how do we design the hash code? For example, one popular strategy would be, you want to consider what's the size of the underlying bucket array. For example, it might be from 0 until big N minus 1. The capital N can be anything. It can be 1 million, it can be 1,000, it could be 100, right? Okay, so now the design would be, you simply say whatever the value is modulo just N. That's one way to go, okay? But exactly what strategy would be better is up to your 2011 instructor. Okay, that's not really covered in this course. In this course, you do not have to design a hash code function yourself. You will always be given the formula you want to use. Okay, but I would say a very typical one is to say modulo the size of the bucket array, and just give you just one more piece of information. And typically, the size should be a prime number. And if you think about what we did previously, we simply said 11 or 13, right? They are prime numbers, typically. Maybe in 2011, maybe when your instructor talk about hash table or hash code, maybe you have to do some programming exercise to implement the bucket array, maybe. But it's not covered in this course. Yes? Correctness proof? Sure, we can do that. Yeah, we covered that already yesterday, but we can do it again. That's not a problem. Okay. Okay, if you just bear with me, I'm just going to get the slides quickly. Yeah, correctness is important. I think I can use, okay, how about this? Okay, there we go. Select 1 and 2. Okay, go back here. Okay, there we go. Okay, so the way to understand correctness proofs is very similar to how you did inductive proof in math, right? Basically, you want to consider two cases. You want to consider base cases. Also, you want to consider recursive cases, okay? In the exam, you may either be asked to prove about base cases separately and also to prove recursive cases in a different part, okay? That's possible. Or you might just be asked to prove, given a method, you want to prove the recursive method is correct. In which case, you also have the same format. Just say prove basic cases first, and then recursive case. Okay, you got to handle basically two categories of cases anyway. Okay, so let's say we talk about collection. Okay, when you talk about collection over here for the base case. Okay, so you talk about either empty collection, empty array, or you talk about an array of size 1. That's typically the two base cases you have to handle. Okay, and also for the recursive case, you have to talk about array or collection with a larger size, which you cannot handle right away. So that's why you got to pass through recursion. Okay. So now, for base cases, they are quite easy to discharge, quite easy to prove. If you only talk about an empty array, usually you should really have the from less than or equal to 2 when they are flipped. So that means you're talking about for example, let's say this. Let's say we are now currently talking about, let's say, all positive, okay, for example, right? If I say I'm calling this particular all positive over here, let me give you some concrete example. Let's say A is an array of size 3. Index 0, index 1, index 2, okay? So now, when you first start off, you're going to say A, and then from 0 to 2. That's how you start with, okay? The first recursive call you're going to make is by, initially you say, I'm going to consider entire array, okay? And then you're going to split that into a subproblem from 1 to 2, and then from 2 to 2, and then you got an empty range, okay? That's kind of the recursive call. Okay, I'll just write it down quickly. That will in turn trigger all. Oh, you know what? Let me just be precise. I just got the method name wrong. It's all positive helper. All positive helper. All positive helper. So let me color that. Initially, we go say from 0 to 2. So that means we want to cover the entire array. Okay? And then the first recursive call we're going to make is like this. We say now from plus 1. So you're going to say A over here about 0 plus 1, that'll be 1. 1 to 2. Okay? So essentially we're saying that we want to also solve this subproblem first before we can solve the entire problem. So 1 to 2 is going to be just like that. Okay? Let's go a little bit more. And then after that, we're going to say all positive helper, the same array called by value, and then 2 to 2. And now in this case, we're going to get 2 to 2. So it's just this one here, right? It's like a sub-range of size 1. But now how can we get to the empty range? You can think about what's going to happen is 2, which is the from plus 1, you get a 3 and then 2, right? So now after this, you get the final call. All positive helper, A, and then you're going to get 2 plus 1, that'll be 3 and then 2. Okay, that's a base case, right? So now in this case, you can see that stops you from going any further, so you don't have any infinite recursion. Okay, so now the from, typically you can see 0 less than or equal to 2, 1 less than equal to 2, but now we got 3 is not less than or equal to 2, so that means the empty range. So 3 and 2 is basically like just empty, just nothing to look at. Okay, good. That's just a pattern for the recursion we are talking about. So now for the base cases, how do you prove the correctness? Two things you have to watch for. Number one, you have to link to the code. Okay, I'll talk about the example. Number one, you want to link to the code. For which you got to give some line number. And number two, also you have to somehow make some arguments. Okay, I will give you an example. Make some arguments. Okay, so these are the two things you do. Let's look at the base cases. let's say we talk about if you want to prove all positive method, right? That one there is simply taking a single array, okay? Usually we try to prove the recursive helper method first before we prove the actual method, okay? So let's focus on this. All positive helper. Let's try to do that, okay? It's going to take an array over here and from and then to. Okay, so these are the two indices, right? And then these are the two base cases. Okay, apparently you can see from should be usually less than or equal to 2, but this is larger than. So we know that this one here corresponds to empty case. And from equal to 2, now over here corresponds to a single element case, one element's case. Okay, empty case. So we got two cases, right? These two cases you can prove separately, okay? So now you can see over here, for the empty case, we simply say return true. Is that correct? So you're basically saying for an empty range of elements, all the numbers there are positive. That's correct. Okay, that's why it's true. So now the way you prove it, you can simply, in an empty array, there's no non-positive number, so result should be true. And we can confirm that in line 3. You can see you're trying to link to the code and also make some argument over here. That's how you prove the base cases. Okay? And similarly, you can say in the case where it's a one element's range to prove, you would say whatever the element is, it should be larger than 0. Okay? In that case, you simply say in an array of size 1, the only element will determine the result, right? That should be in line number 4, which is here. Are you okay with the base cases? Okay, good. So now, how do you prove the recursive case? The way to prove it goes like this, okay? The pattern goes like this. In general, if you have this particular range of the array to consider, this range is from to 2. That's a range, okay, the pink one. The entire range. But somehow, this range is too large for me to consider right away, so we need recursion. We're going to divide this problem into subproblems, okay, into two parts. One part is, I'm going to draw in blue. This is the first part, which is just A from, which is just a single elements, okay? And then the second part is, I'm going to draw in green. The second part over here, the remaining part. So this part here is basically A from plus 1, A from plus 2, all the way to A 2. Okay, you can see we talk about two ranges, right? One is the green, one is the blue. The blue part is almost like a base case. We can calculate right away just to see A from, is it larger than 0 or not, right? In this particular example. What about the green one? The green one, if you talk about programming, you're simply just making some recursive call. When you want to prove it, you can simply assume the recursion is just going to return back to you the correct result. Okay? So what you would do is, the strategy would be make recursive call as the inductive hypothesis, which means I am assuming that when I am trying to make recursive call on this particular sub-range, it's guaranteed to give me back the correct result. It's guaranteed, okay? How do we say that? Okay, let's see that, okay? So now that's why you see something over here. Inductive hypothesis over here to say, now, all positive helper from plus 1 and 2, right? You can see it's from plus 1 and then to 2, right? That's kind of the, from here. Yeah, exactly here. This particular sub-range is from plus 1 to 2, right? Exactly that sub-range. We're saying that that's going to give me the correct result, which means it's going to be true if everything in that particular range are all positive. Otherwise, it will give me false. That's something I simply assume. I would say this part here might be the most tricky one, because for every recursive method you might be given, your inductive hypothesis might be different. Okay, that's why maybe try to do the practice question I gave to you as well. That one has a different inductive hypothesis. Okay. Once you have done that, the rest will be easier. Okay, the rest will basically be, let's go back to the code. Okay, if you look at this line here, line number 5. Else part simply means none of the two base cases actually is satisfied. So I will simply say I'm going to return a from larger than 0, and also all positive helper on this. And then I'm going to use a conjunction. Okay. So now if you look at this particular code, which somehow combines the result from the recursive call with something else and try to combine it together and then return. Okay. Is this line correct? That's something you want to argue. Okay. So now here's the thing. Thinking this way. This one here, the right-hand side of the conjunction is exactly the same, has exactly the same range as the inductive hypothesis. Okay. According to the inductive hypothesis, we know that it will return true if a from plus 1, a from plus 2, all the way to a 2. Basically, from plus 1 is here, and 2 is actually over here, right? We're saying all the elements there are all positive. According to inductive hypothesis, we can just use it. And then you can see this part over here is really trying to compare just to see if a from is larger than 0. And then basically that's what we're doing. If I know whether or not this particular element a from is larger than 0, if I also know whether or not the rest of the array, which is a from plus 1 until a2, if I know individually whether it's all positive, I can simply combine it using conjunction to see overall if that's all positive. And that way of combining the result is simply just correct. That's why you have to argue. Okay? That's why you will see that over there, we are simply trying to use the inductive hypothesis over here. That's why you can read it a bit further. Okay, so finally, what we have just proved is just the correctness of all positive helper. Okay? Finally, you want to prove about the overall this method here, which the user will actually call. How do we prove that? Given any arbitrary from and to, your recursive helper method is always going to work. But now, overall, it's simply just going to call 0 and then a.length minus 1, which essentially you can think about, if this is my array, arbitrary array, 0 until a.length minus 1. And then the way we call that, the recursive helper method, is by using 0 and a.length minus 1. So this will be the from, and this will be the to. So that's going to cover the entire array for sure. So that's why it's also correct. Okay. Does that help? Okay. Yeah. Maybe try to read the solution for the practice question as well to see if there's got any more questions. Yeah. Do you guys know about the strategy of answering multiple choice questions? So if I were you, I'm thinking about, I was a student many years ago. If I were you, I would do the following. Okay. You got 180 minutes, right? Let's say, for example, if you got 40 multiple choice, I'm not saying you will get, I'm just saying let's say. Okay. Huh? I said you will get between 40 and 50 roughly, right? He said 40, exactly? Yeah, some range, right? Yeah. Let's say you got, did he say 50 or 40? Okay, let's say 50. Okay. I don't think he really meant you will get 50. I think let's say. Yeah. Anyway, let's say 50. Okay, that's not important, right? Doesn't matter. Okay. Let's say you got 50 multiple choice, right? Let's say maybe you got about 5 written questions. Let's say, I'm not saying you will get 5. I'm just saying let's say, right? Okay? This is what I would do, okay? I'll definitely start with multiple choice, okay? And then I would say if a question is going to take me more than 2 minutes, okay, this is how I would do it, okay. You can actually, once you see the question, you can kind of decide how much time it will take you to really answer the question, okay? I'll say no more than 2 minutes on each question. If you see right away, if the question is going to take you more than 2 minutes, I'll say skip it for now. Okay, and then do the first round and complete all the multiple choice that you can answer immediately with confidence. Do that first. Okay. Again, that's how I did it when I was a student, right? I'm just saying, you might do that too. Complete all the questions that you can answer within 2 minutes. Okay, and skip all those. Okay, but of course make sure you come back to them. Okay, and then after that, hopefully you got at least half of the time for the written question, right? At least 90 minutes for that. Hopefully, I'm just saying hopefully, right? And then for each written question, again, you want to think about how much time you want to dedicate to it, right? Again, maybe about 10 minutes each. Okay. After all these, you can now go back to answer the multiple choice. Because for the multiple choice, what's the worst case? You can still guess, right? But for the written question, you cannot really guess. You got to write something. Okay. I also would say start with the multiple choice. I can say there are certain multiple choice questions there that require quite a bit of thinking. Basically, when you see them, you might want to decide, oh, come back there. Okay. But you may have your own strategy. I'm just suggesting mine. Okay, any more questions? Well, time flies, right? Yeah, I didn't realize time flies pretty quickly. Yes?
What exactly is a sound hash function?
A sound hash function. Can you remind me where I said it?
I think it's in the slide.
In the slides? Okay, let me see. If you can tell me the slide number, that'll be very useful. Yep. Do you know the slide number? There's something about, okay, hash function. Let me see. Okay, the question was about the hash function. The sound, okay.
45.
Okay.
Yeah, probably.
Oh, what I'm saying is, okay, let's say when the hash code for K1 and the hash code for K2, let's say, if they simply give you the same result for K1 and K2, now you got two possibilities. You can either be because K1 and K2 are simply different keys. For example, let's say 23 modulo 11 will give you 1. And also 12 modulo 11 also give you 1. So they're two different keys. So in that case, you will satisfy the first one. Okay, I'll write it down. Okay, let me, I'll write it down on the iPad and I'll show you. Hash code of K1 equals hash code of K2. Okay. Okay, let's say the way we calculate the hash code of K, assuming that K is an integer, okay, will just be K modulo 11. Okay, so now basically we're talking about two cases. Okay, let's say over here, if we simply get hash code of, let's say 23 is equal to the hash code of, let's say 34. Agree? Okay, but the hash code will just be 1. Okay, I'm sure you know how to calculate that. Okay, so this one is good because it simply means collision. even though we got different keys over here, but the hash code is simply just the same. That's collision. Okay. The only other case you can have is to say, if you try to use the hash code function twice, for example, right? The first time I'm going to say hash code of 23. And also, if you try to use hash code again, also you get 23. Okay? Should you get the same result? Mathematically, of course, right? It's a no-brainer, right? Because you're trying to say 23 modulo 11, and also 23 modulo 11, okay? You'll simply just give you the same result. So when I say sound, it simply means correct. It just give you the same result every time. Okay. Yeah. Okay. The same result for the same input. Yeah. Okay. Yeah, you should really know about the properties for the hash code. Make sure you know about it, right? So what does it really mean to have collision, and what does it really mean for other cases? Yeah, you want to study that a little bit. You can ask me maybe again. Yeah. Yes? Ah, good question. Can an abstract class implement the interface? You know, it's a good question. It does not happen often. If you want to have, let me double check with this. Are you coming on Thursday? Okay, let me double check with this. I'll get back to you. Okay. The question was, can you, usually when you implement interface like a, let's say point, right? Let's say it can be either polar points or Cartesian points. Usually the subclasses under interface will just be not abstract because they got to implement all the methods. You're basically asking, is it possible to have an abstract class that implement an interface partially? Okay, I'm not too sure. Let me check it out. Okay, I'll get back to you. Okay. Any other questions? I'll just write it down for myself. Okay, guys, by the way, so even though I think I like the question you have so far. It's mainly about recursion, asymptotic analysis, pretty much the later half of the course. Don't forget, things might also be covered before the reading week, right? Especially since we spend so much time on the aliasing classes and objects, you want to make sure to review those as well. Also, inheritance is really important, right? Okay. Okay. Just make sure you do that. Okay. Any other questions? Yeah. The Java library, I would say make sure you know about array list and also know about the map, the hash map that we talk about. Then you'll be fine. Yeah. Yes. Oh, you know what? You wouldn't have to write any code about insertion sort and selection sort. You don't have to. I think the main lesson from the insertion sort and selection sort, insertion sort, the main lesson is, given the Java code, can you derive the tightest asymptotic upper bound? I think that's the main lesson from those two sorting algorithms. Okay. Yeah, you don't, okay, we wouldn't really ask you specifically how the selection sort work or how the insertion sort work. But given the fragment of code that looks like selection sort, you should be able to come up with the asymptotic upper bound, right? Like how we did it in the last class. Yeah, that's something you should know. Yes. Any other questions? Yes. Oh, no, don't worry. It's one of your colleagues posed a good question. I don't have an answer for now. I'm going to answer that later. Yeah.
Are abstract classes typically a subset of like interface classes?
Well, you can think about, think it this way. Think about interface like a special case for abstract class. For abstract class, you got typically for abstract class you got at least one method that's not implemented, just a signature, just a header. Interface is like an extreme case where all the methods are just headers only, like a special case. That's how you can think of it. Yeah. Mm-hmm. Yes. Okay, a little bit, sure. Let's use some hierarchy over here. A, D, let me just make right to the point. Okay, so let's now create 80 branches. Okay, let's say we have that. And then let's say over here we got DM, like a method. Okay, let's say that one there is simply just print out, print the implementation, just print DM. Okay, and then over here for B, we redeclare the DM, which means we override it, right? And now over here, oh, you know what? Let me change this just a little bit. Okay, print D.dm, which means the DM from D. Okay, and the DM over here that's overridden will say print B.dm. Right, you can see the source class is different. Okay, and also we got BN, in which case we're going to say print B.bm. Okay, let's do another class. Okay, and for A here, again you got to overwrite DM and then print A.dm. And then over here you're going to say AM print A.an. Okay, let's say this is set up. Okay. So basically, okay, not to be confused, you got one method for here, you got two methods here, you got two methods here. Okay, don't get confused. Don't forget, of course, you got some overriding. Okay, so static type is simply the type you declare the object to be, right, the variable. Okay, let's try various example. Okay, start with a simple one. The object one. New D. Okay, does it compile? Wow, that one could be quite trivial, right? Good. Okay, and now if I say obj1 dot bm, what's going to be the output? Huh? It doesn't compile? Does it compile? Be careful, right? It doesn't compile. Why does it not compile? Static type is D. Does D support AM? Does D support BM? No. Okay, be careful, right? Okay, doesn't compile. Very good. Because the static type over here is simply just D, right? And does not support BM. BM is only supported at a lower level. Okay. So now, if I say obj1 dot dm, does it compile? All right. When I execute the code, what's going to be the output? Okay, first of all, let's get something clear. How many versions of dm in this inheritance hierarchy? 3 versions. Okay, let's highlight it. Okay, 1 version here, 1 version here, 1 version here. Which version to be called depends on the dynamic type of the objects, which might be switched depending on the context. And you as a programmer is responsible for keeping track of the dynamic type, not the compiler. It's an undecidable problem. Okay. Good. Okay, guys, I agree with you for sure. This one here is going to tell you d.dm. Okay, I agree. Okay, let's try the following. If I say over here, purple, okay, obj2 new a. Would you agree that compiles? Okay, thank you. And then if I say, first of all, obj2, okay, it's obj2 dot dm. Again, we got 3 different versions, right? What would be the output? A, should it be A or B or D? Depends on the dynamic type, right? Okay, dynamic type is over here. Okay, so that should be, okay, A dot dm. Okay, so here comes my question. These are just warm-up. I want you to consider 2 scenarios independently. Scenario number 1. If I say obj1 is assigned to obj2, and then I say obj1 dot, okay, give me one moment. Okay. Scenario number 2. Independence. Okay. You know what? Let me try with something a little bit easier. Okay, and we can try to build it up. Okay. Let me say over here, I'll simply say dm. Okay. Scenario number 2. If I say obj2 is assigned to obj1, okay, and then I would say obj2 dot dm. Scenario 1 and scenario number 2. Think about they are executed independently. Okay, they are not really one after another. Okay. Will they both compile? Okay, first of all, let's figure out why both of them should compile, at least for the assignment, right? Again, to figure out if they should compile or not, static type for obj2 is D, which is a descendant class of the static type for obj1, which is also D, right? Similarly, okay, for the other one. Good. Now, question for you. If I execute these 2 fragments of code independently, am I going to get the same result? Well, they're both calling dm. They're pointing to different objects, right? Okay, now, for scenario number 1, okay? Scenario number 1, we're basically saying obj1 was pointing to D to begin with. And obj2 is now was pointing to A originally, right? And for scenario number 1, obj1 is now reassigned to obj2, right? So now that means obj1 is now pointing to A. So now when you say obj1.dm, what would that be? A.dm. Agree? Okay, please review that. Okay, A.dm. First of all. Okay, scenario number 2. Okay, I'm going to use a different color to show you. Okay. Scenario number 2. Okay, again, we start with obj1 pointing to D, okay, to begin with. And also we got obj2 pointing to A to begin with, okay. And now what we're doing is we say obj2 is assigned to obj1. So that means obj2 is now going to point to obj1. So now if I say obj2.dm, well, apparently I'm getting something different, right? Because now the dynamic type is simply D. So would you agree I'm going to get D.dm, okay? Guys, any questions? Are we okay? Okay, let me modify this slightly. Okay, let me think it through. Give me 10 seconds, okay? Okay, D and A. We want to do a little bit more, okay? You know what, I think it'll be fine. The one I'm thinking about requires a little bit of casting. That'll be too complicated, okay? But it's a very quick review, of which version you should call, okay? One more thing you should really review. Let me just point to you, okay, ask me again. Make sure you also understand about when you talk about dynamic binding, right? You basically calling the version as closest in the closest ancestor. Okay, so you may also want to review this particular slide, and then I'll take your question. Okay, if you go to the inheritance lecture, go to the very final topic that we talked about. Okay. Oops, sorry. Inheritance. Okay. Okay, let me just go all the way to the end. Okay, remember the example we talked about over here in equals? So maybe we want to review these 1, 2, 3 different versions about how you call the equals method. That can also further emphasize, strengthen your understanding, dynamic binding. Okay, yeah. Questions? Yeah, go ahead.
What about when you're calling a method that takes in a parameter, like the compile time error and the runtime error?
Oh, parameter, right? Okay, let's build on top of that. Okay, let's just see one example here. Okay, let's say we got this particular hierarchy. Oh, I just already rebuilt it. D, B, and A. Okay. D, B, and A. Okay, let's assume that. And then we have things like, let's say we got another class. Let's say class just called C. And over here, I'm going to say, okay, let's say this. I have an array of type B. Okay? Let me say array, just say array. Okay, and then I have a method over here to say add objects. Okay? And then, first of all, let me give you different options here. Okay? If I say add object here, D, I'll build it up. Okay? Now, can I say, assuming that we got a counter, okay? So now you can say integer number of items. Okay? Number of items. You should be very familiar with these patterns already. Okay? Assuming that we have done that. Okay? So now if I say A at a position, number of items is assigned to B. Let's start with this. Okay? Is there any problem for the code so far? Assuming that we got a constructor for this class C over here, where in the constructor we simply initialize the array of certain size, let's say. Okay. Do you see any problem for this add method here? You do? Yes. Tell us. What do you see? Okay, so which line do you think is problematic? 1, 2, 3, 4. 4. Okay, good. So this assignment is not quite valid, right? Because over here, okay, first of all, this method is simply not right. Because the static type of D is D. the static type for this particular array element over here is B. D is not a descending class of B. Okay, so this method here is simply not compilable. Okay, first of all, I want to start with that. Okay, and then let's talk about maybe some different choices for the parameters. Okay, let's try different options. Okay, let me say I want to do this. Void, also called add, right? And then I will simply do B over here, and then B. A at position NOI is assigned to B. Of course, you got to do NOI plus plus. Now, is this method okay? Okay, good. If you follow the same logic, work out the static type for B and work out the static type for this, you will see the rule actually is satisfied. Okay, let's say that's for that. Now, let's have just one more class to bring everything into play. Okay, questions first. Yes.
It would have been fine as well, but if you use a NOI equals like
Oh, yeah, exactly. So what you're saying is, if hypothetically, if I simply change this type to be A,
oh no, I'm at the
you mean here?
yeah.
If I
Sorry,
change
no, I'm at like inside the loop where we assign
the loop, there's no loop.
brackets.
This one? This method you're talking about?
Yeah.
So what do you want to change?
A like with the square brackets NOI equals A.
Okay.
Instead of B.
You can just say A here,
Yeah.
but there's no A.
Oh, what?
There's no A. Is there A?
No, I'm saying at the DB A.
DB. Oh, okay. Basically, you're saying that you want to replace this just by A, right? Is there a variable called A? Yeah, exactly. Yeah, I see what you mean. Yeah. Okay, if you really want, okay, how about we do, okay, just for the sake of illustration. Okay, no worries. That's fine. That's fine. If you really insist, let's do the following. A and A. Let's say for some reason we want to do the following. Don't ask me why. Okay. A NOI is assigned to A. That's what you want, right?
Yeah.
Now, would it compile? It would, right? Still. Because A, the static type is simply just A. NOI, static type, remains to be B. Okay? A is a descendant of B. Okay? Yes? Why am I doing this? I don't know. Okay. Just put it there. Yes, question.
Can you go over in terms of valid and invalid substitution?
I can go over that. Let me just finish this example here. Yeah. Mm-hmm. Okay. Okay, let me just continue a little bit. Since you asked about a passing parameter, let me finish that. Okay. Okay, we're okay so far. So what I will do is I'm going to just add one more class into play. Okay. Would it fit? Yes. Good. So now I want to do just one more class. It's an app. Okay. Okay. And somehow we have a main method here. Okay, so now what I will do is I'm going to do the various passing. Okay. Object 1 is, well, this one going to be interesting. Okay, let's say D here. Ah, okay, now I got some very interesting thing to try. Okay, so let's say object 1. For this part, I'm just going to, for the right hand side, I'm going to make it straightforward. Just say D. Okay? And then, oh, it doesn't matter. What I will do is I will make it new A. And we know very well it will compile. Okay? And then let's say we initialize C. Object C is new C. Okay, just creating an object of that. So now, can I say, I think it might be easier for you to see that this way. Okay, let me just change that a little bit. Okay, I think that's better. Okay, So now if I do things like object C, okay, dot add. Well, remember we got two parameters, right? Thanks to you. Now we got a more interesting example here. Okay. Should this line compile? Well, apparently you got two parameters, right? You got to talk about each one of them. Will both of them give you errors, or just one of them, or none of them? You may want to think about it this way, okay? That's the first one here. Call by value tells us implicitly there will be some assignment to be done, right? Call by value tells us implicitly, we're going to say, okay, I'll put it here. Implicitly, B is assigned to obj1, implicitly. Is that going to compile? Apparently not, right? Because B over here is static type is B. But now you're passing something statically is just D. Okay, that's not good. That's about parameter passing, okay? So this one is no. How about this guy here? Also no, okay? It's simply because now we're expecting A, but now you're giving us, again, D, statically. So that's not going to pass. Okay, one more, okay? What if I got something like this? obj2 mu A. OC dot add obj2 obj2. In the previous example, we know that this is not good, this is not good. How about the new one? Are both of them going to give you errors, or just one of them? One of them? Which one? Left one or right one? Let's see. Okay, you kind of get the idea, right? Okay, let's try quickly. For this guy here, obj2 statically is B, static type is B. And now implicitly, we're going to have B is assigned to obj2. And B statically is B. This one statically is B. So that's fine, right? Okay. How about this guy over here? Not good, right? If you do the same reasoning. Okay, I'll do it, just in case you are still not following. Okay. Static type for obj2, again, is B. And now we are doing implicitly, A is assigned to obj2, right? Call by value. A is assigned to obj2. A is A. obj2 is B. Can you assign B to A? Apparently not. Even though dynamically it's pointing to A. But for compilation, it doesn't matter. What can you do in order to make it work? Casting. How do you cast? That's the final thing. Again, this one is not going to compile, but if I do the following, if I say oc.add, I know that I can simply pass obj2 for the first one. Okay, it's going to satisfy this, no problem. The second one, I'm going to do a casting. I can cast that into A, because I know very well it's dynamically A. Okay, this will compile. So it might be a very nice exercise for you. Try to reproduce this in Eclipse. Okay, just convince yourself. Okay. All right. Andrew asked about maybe something about substitution. Maybe ask me as a first question on Thursday. Okay. Guys, any short questions? We still got 5 minutes if you wish. Short questions. Yes.
Does get class return
Get class returns
dynamic type?
dynamic type, I think. Basically, the object that you're pointing to, then dynamically, which class is it pointing to? Which objects? Yeah. Are we okay? All right, let's call it a day. All right, we got final review session on Thursday. Okay, I'll send you a reminder. All right.